Okay, this is a quick video about electrostatic energy, and it's concept-driven. I want to show you how, rather than thinking about energy belonging to an object, it really comes from the interactions between objects, and that rather than talk about the objects themselves, you can assign the energy to the interaction, and then that in turn leads us to be able to talk about energy stored in a field. So if energy is real and fields store energy, then fields are as real as energy. I'll do some calculations along the way too, just to give you a little bit more bang for your buck, but I'm mainly interested in concepts in this one. There is a lot of math in this video, and you can follow it as closely or as casually as you like. All right, the first thing to think about is, if I have a point charge and it's all by itself, does it have any energy? I would say no, there's no potential for it to move anywhere because it's not interacting with anything, so it has no energy. If you remember the equation you have the potential energy of a charge is given by the charge times the potential. And really, when we say the potential, we mean the potential from other charges. It doesn't really interact with itself. And so let's do that. Let's bring in another charge that it can interact with. Okay, great. So now this charge Q2 creates an electric field. That electric field is felt by charge Q1, and it produces an electrostatic energy. Okay. Of course, the other thing we can say is, well, look, doesn't Q1 create an electric field, and doesn't Q2 have energy as a result of that? Yeah, absolutely. In fact, charge 2 also has energy. And if you know the formula for the potential of a point charge, you know that these energies are the same number. So that's kind of weird that both have the same energy the instant they see each other, right? A question is the total energy of the system the energy of each one, or the sum of the energies between them, or some other number entirely? In other words, how much energy is in my system? So I want to take a step back for a minute and go back to mechanics land. When you had an object on a spring, you used to say that this is the potential energy that the object has. And we mean that, well, you could do some work on that object as the spring pulls it in, and then you'll develop kinetic energy. That's what we mean when we say that it has potential energy. And so we say, okay, that guy has kinetic energy, but what about the spring? Does the spring have kinetic energy? Normally we say the spring doesn't have any mass, so we don't even think about it. And then I say, this is also a funny thing. Does the wall have kinetic energy? Of course not. The wall doesn't move at all, so we never even consider it. But I want you to consider that this is an interaction between two objects. And so really, in order to have the energy, both objects need to be there, and maybe they're both important. So what I want to do is I want to replace the wall with another mass that can move, and I want to answer this question very carefully. Is there twice this number or that number stored in the system? Okay, and I'm going to do it carefully. All right, so first of all, let's give them both positions, x1 and x2. Okay, that's where they start. The spring will pull them inward. They'll both develop some velocity, and they'll land at final positions, x2 final and x1 final. Now, one thing to keep in mind here is that in this system, there are no external forces. And what that means is that if this guy and this guy have the same mass, then they need to move the same amount. That way, the center of mass of the system doesn't move. Another way to say that is, look, this is an internal force. By Newton's third law, it causes equal and opposite forces on both of them, and if they're the same mass, they have to move the same amount, and that's another way to say conservation of momentum. Okay, so now let's, by conservation of momentum, say that since, let's call the center, we'll call the center x equals 0. And so what that means is, however far this guy is to the left, this guy has to be the exact opposite to the right. And so what I can say is that x initial equals twice x2 initial. Now, what do I mean by that? I mean that the total stretching of the spring, x initial, is equal to this distance, which is x2 initial, plus this distance, which is x1 initial, and those actually have to have the same magnitude. Okay, now let's find the work. Let's find the work done on both objects. This is the work done on Q1, and this is the work done on Q2. Notice they experience the same force, but one of them has a minus sign because on this charge, the spring pulls to the left, and on this charge, the spring pulls to the right. Notice something else. This guy gets integrated over its position. This is F1 dx1, and this is F2 dx2, okay? So I have two integrals over two different integrands, right? And what I want to do is start to do some algebra to put this all in terms of one thing, okay? So again, from Newton's third law, I know that the following: x1 equals minus x2. Whether that's the initial value or the final value, they always both have to sum to this center of mass at x equals 0. This also implies that dx1 equals minus dx2. And so this guy in this equation, what I do is I plug in for x1. x1 is negative x2, so x2 minus negative x2, I get 2x2. And then over here, I'm swapping out the dx1 and I'm swapping out the x1. And the effect of that is that I get, again, 2x2, but then I swap out the dx1 and that becomes negative dx2, hence the negative there. This is mostly algebra, okay? So what I'm going to do now is I'm going to perform these integrals. It's a pretty easy integral. They're both over dx2, so it's just an integral of x, really. And so I end up with something that looks like this. So that's what that integral shakes out to. Now, let me just clean this up. There's a lot of stuff there. I'm just going to rewrite it. Okay, so that's the exact same thing I just had. And then I'm going to simplify by, again, saying that x1 final squared equals x2 final squared, and the same thing with the initial. And so basically, I have two of the same term. Now, the thing is, that looks like this. And actually, I said earlier that, look, x initial is 2 x2 initial, and x final is 2 x2 final. That means that if I square x2 final squared, that's x2, the total extension of the spring, divided by 4. And so this is fascinating. What I've done is I've shown that the work done on both objects is actually equal to this initial energy that I thought was stored in the spring in the first place. In other words, it doesn't matter whether it's attached to a wall or to another charge. That is how much energy is available to the system. Of course it is. Why would putting another charge there somehow create more energy? The energy is stored in the interaction between the two objects, and in this case, that means it's stored in the spring. Another way to say that is they share the energy. Another way to say that is the total amount of energy available is the total amount of work done that one has to do in order to assemble this distribution. So let's go back and let's return to our two charges. Now I say, is U total U1 plus U2? No. The point of the spring is that the total energy of the system is just the energy that each has. The energy comes in pairs. It comes in pairs. And in this sense, the total change in potential energy of the system comes from minus the work done by the field. So before, I looked at the work done by the spring. Now I don't have a spring anymore. Of course, I've replaced the spring with this weird thing we call a field. Okay? Before we do anything stranger and more abstract, let me just do a concrete example for you. Okay? So if I have 4 charges and I want to know the total potential energy of this system, well, I know that each pair of charges interacts with each other, and so each pair has energy. I've got U12, U13, U14, U23, U24, and U34. Okay, so if I were to imagine that there were some distances, I don't know, A and A and A and A, you can make them whatever you like. Well, then I know what to put here. Okay, and so I can re-express that in terms of potentials. And so that's what I do. So long as I know these distances, I simply add all these things up. I want to show you something really weird, and I need it for later, which is why I'm going to do it. I'm going to say that that is half of, instead of counting the pairs, look how I go 1, 2, 1, 3, 1, 4, and then I go 2, 3. I never do 2, 1. Now I'm going to. Now I'm going to include 2, 1, and I'm going to include 1, 2. And you might say, aren't you overcounting in that case? Yeah, absolutely. I'm deliberately overcounting, and I'm putting a 1/2 in because I'm double counting everything. And you might say, wow, that sounds like a really weird, crazy thing to do. It is, but I'll show you the payoff in just a second. On the one hand, what I now get to do is I get to say this is 1/2 each charge times the total potential that each charge sees wherever it is. In other words, Q1 sees a potential from Q2, Q4, and Q3. I don't have to worry about pairs anymore. I simply calculate the value of the electric potential due to other charges at any given spot, and I look at what size charge I put there. So it lets me write this as kind of a nifty formula as 1/2 the sum of each charge times whatever potential each charge happens to find itself in. Okay, so what's the payoff of this? The payoff of this is that if I want to know how much energy is stored in a uniform sphere, I don't even know how to find pairs anymore. There's an infinite number of things. I can't index this, right? But what I can do is figure out what the potential everywhere in a sphere is. Everywhere in a sphere. Okay, so how do I do that? Well, I imagine each piece of the sphere is made up of a little bit of charge, dq, and I can use, amongst other things, an integral to find the total potential everywhere in the sphere. So there's a couple things we have to do here. Number one, we have to figure out what dq is. That's no problem. dq is charge per unit volume times a little bit of volume. And the other thing I have to do is I need a formula for v inside of a uniform sphere. And that's not a problem, because we already know Gauss's law, and I've done videos in the past where I work these things out, and I'm going to keep it as clean as I can in this video because there's a lot of math coming down. So you can go elsewhere to see that, but that is the electric field. This is for outside the sphere. This is for inside the sphere. And what I want to do is I want to find the electric potential at each point in the sphere relative to infinity. And so the way I do that is I integrate the electric field. I go from infinity to r, and what this produces for me is V of r. In other words, right where this charge is, there is a V of r created from the entire sphere, and this charge feels this V of r, and once I know that V of r, I can go back and add over all the energies of all the little pieces of the sphere. Okay, so in this case, I'm just going to do this integral, and if I do that integral, I end up with something that looks like this. And what I want to do is just clean this up a little bit. Like I put kq over r squared here because it's basically just Coulomb's law. But let me express everything in terms of the same kinds of things. So I'll express kq is 1 over 4 pi epsilon naught. Q is rho times the volume. So these are just some small simplifications I'm going to make, and then cleaning up, algebra, and then great. I now know the potential inside of a sphere. So my job is to take this potential and punch it into this formula and see what I end up with. Okay, so let's do that. So the way I'm going to envision it, rather than picking cubes of charge, I'm going to say, look, I know that the potential only depends on the radius, so why don't I pick huge sections of charge dq that all have a fixed radius? Each piece of charge dq has the same potential, and so I can find the energy of this entire shell instead of a little tiny cube. Okay, so in this case, I just need dv. dv is the volume of a little spherical shell, which is the area, 4 pi r squared, times the thickness, dr. Okay, now I'm ready to use my formula. So I've got U total is 1/2 v dq. I can plug in for v. I can plug in for dq. And now I've got an integral to do. This integral is not so bad. These are all polynomials, guys. Okay, so I end up with something that looks like this after a little bit of simplification. And then I can simplify further. And I end up with something that looks like this. Now, I have this guy rho squared here. If you've seen this problem done elsewhere, I'm going to get rid of rho squared just to show you the result in standard form. I'm going to replace rho with q over, so rho is q over 4/3 pi r cubed. If I make that substitution, that's the result you'll see if you Google how much energy is stored in a sphere, right? Okay, so that's how you get that answer, okay? So in other words, I have this sphere, and I just figured out the total energy in the sphere. And the question is, what is that energy? Whose energy is that? And it's just like the spring. Every piece of mass in there shares the energy. This is shared by every single piece of mass inside this sphere. But I want to actually go a step further, and I want to stop talking about the pieces of charge, and I want to talk about the interaction. Where is the spring here? The spring is the electric field that causes the charges to either attract or repel each other. And so I'm wondering, is there a way that I can express the energy in terms of the electric field? Like, if you look at this formula, the force, the interaction force, is kx, and it's not hard to see that the kx is hiding in there, right? I want to know, is somehow is the electric field hiding in my U total? And that's what I want to do. And I need to do a little bit of vector calculus to do it. And if you know vector calculus, enjoy. If you don't know vector calculus, just hold your breath until the end. It'll go really fast, and I'll show you the big conclusion I wanted to make in this video, okay? So here's what we started with. This is the equation I said produces the total energy in a system. The thing I want to point out is from Gauss's law, del dot E is the charge density divided by epsilon naught. That's just the differential form of E dot dA equal Q enclosed over epsilon naught. This is our differential form of that, right? Okay, so I'm going to make that substitution. I'm going to get rid of rho because I want to stop talking about charge. I want to just talk about fields. So when I make that substitution, I end up with this integral instead. Okay, and now I'm going to do something really weird that I never would have thought of unless I'd already seen someone do it. But if you're good at vector calculus, you'll observe that if you do product rule with divergence, it looks something like this. This is just product rule. It's a fancy version of product rule. That's what integration by parts is. When you do integration by parts, you're actually using product rule inside of an integral. In other words, del dot E, this thing, is equal to the left-hand side minus this. That is why you end up with a minus sign in integration by parts. You're actually using product rule backwards. So I'm going to do integration by parts, also known as product rule, and I'm simply going to substitute in this thing I have, okay? And then I'm going to do a dirty little trick. I'm going to say that the integral of the divergence over some volume is actually equal to the product of the two things over the area. In other words, to go from here to here is divergence theorem. This is the same theorem that lets you convert from the differential form of Gauss's law, E dot dA equal Q enclosed over epsilon naught. This is the same theorem that connects these two. All I'm saying now is I'm just going to use that same theorem. I'm going to take this piece, instead of integrating over a volume, I'm going to integrate over an area. Now, the thing to keep in mind is I actually haven't said what volume we're integrating over. But if you think about it, if we just return to the original beginning, I'm integrating over wherever there was charge, right? And so I could stop my integral at R. I could do that. Or since there's no charge out here, it really doesn't contribute anything to the integral anyway. So I may as well actually take my integral over all space and just make the claim that rho equals 0 for R greater than R. In other words, that's definitely not going to change what the integral is. Well, what does that buy me if I do that? That buys me that if I'm actually taking the integral over all space, what is this integral? This integral is the integral over a surface which encloses that space. But if I'm going over all space, that means that this surface I'm integrating over, has an infinite radius. If that surface has an infinite radius, then when you get infinitely far away, the electric field is 0 and the potential is 0, and therefore that whole integral is 0. What that means is this little trick, integration by parts, actually puts me in a position where I can express the total energy of the system just in terms of the square of the electric field, over an entire volume, right? So that's a pretty big deal. What does that mean? That means that I can express the total energy of the system by talking about these guys. I don't have to talk about this guy at all once I know the electric field anyway, right? So what does that mean? That means that the energy is in the field. And if you wonder what I mean by that, this is really what I want to sell you. Here's a little small region of space. It has a particular volume, V. I can say if this is the total energy, then the energy per unit volume is whatever's inside the integral. In other words, don't integrate it. And then this will tell you the energy per unit volume. I'm telling you that inside of this cube, even though there's nothing there, there's energy because the cube has volume and there is a non-zero electric field there. Okay, so that's the big idea. When you see this in introductory physics textbooks, they normally say it can be shown. Well, this is how you show it. It's a bit above your standard introductory physics course. You need a little bit of vector calculus for it. But this is the big idea. And so the big concept is the energy is stored in the field, not in the charges themselves. Okay, hopefully this video was more helpful than confusing.